For our last video, we are going to be analyzing the two functions p of n and q of n. P of n is 3 times the natural log of 2 plus n, take away 7. But q of n is the inverse of p of n. Our goal is to find our q function so that q of n is actually the inverse of p of n. Similarly to the previous video, our goal is to first find q of n to be the inverse, and then we're going to analyze them against each other using composition of functions. So in math, our procedure never changes. The way our numbers look change, but if you keep the logical processes the same, you'll find that patterns start to arise. So yes, our p function looks a lot different. It's not just multiplication and addition anymore. We actually have a natural log in there. But again, our procedure doesn't change. So let's break down our p function into the operations that make it up. Our first part of p of n is actually 2 plus n. But I'm actually going to flip this around using the commutative property and write it as n plus 2. And you'll see why it makes a little bit more sense later. The second part of our p function is then the natural log of a number. Our third part of n is then we're going to triple that number. We're going to multiply it by 3. And then our last part of our p function is that we're going to take away 7. Similarly to the video before, we want to find the inverse of each of these parts. So the inverse of the first part of p is, instead of adding 2, we're going to take 2 away. The second part, in the natural log of n, the inverse of the natural log is actually using e. E is a special number, it's a transcendental number, and I'm not quite sure how to talk about it, so I'm just going to say e to the power of n. And then the third part of our p function, to find the inverse, instead of 3 times a number, we're going to 1/3 of that number. And the fourth part, the inverse of the fourth part would be, instead of taking away 7, we're going to add 7. So our q of n function, which is actually the inverse of p, we're going to start with our number increased by 7. We're going to then multiply it by 1/3. We're going to have it on Euler's number, x raised by e, and then we're going to take away 2. So our q of n function is actually e to the power of 1/3 of n increased by 7, take away 2. Our mini goal was to find what q of n is, because we know it to be the inverse of p of n. So we did a really good job at breaking down the operations and building the inverse, but let's check to see if it's valid. So in order to check for validity, we use the inverse to obtain the identity, and our goal in this problem would be to end with n using composition. So we're going to take our q of n function and we're going to put it in our p function. So we take our e raised to 1/3 of n plus 7, take away 2, and inside of our p function we see that we are going to increase by 2 and then have the natural log, it being multiplied by 3, and then finally taking away 7. Within that first line, there's a lot going on, But in all of that craziness, I can actually see that there is, at first, the additive identity. With that take away 2 and increase by 2, there are 2 zero pairs that I found. So, great. Let's move on. Again, I'm going to rewrite everything. 3 times the natural log of e raised 1/3 quantity n plus 7, all take away 7. Okay, so then what do we work with now? Well, ln, the natural log, and e, they're inverses of each other. So they actually become 1. So I'm left with 3 times 1/3 of a quantity n plus 7, take away 7. And this seems much simpler now. I see that there is a 1 pair. I can have that drop out because a 1 pair creates 1. It's the multiplicative identity. So I'm left with the quantity n plus 7, take away 7. And this is great. I see that there's the additive identity as well, just like the beginning of the problem. Plus 7, take away 7 is 7 zero pairs, and I'm left with just the quantity n. So through this composition, I can see that my p function and my q function are inverses of each other. But I want to check the other way as well. Let's compose p within q. So my q function is kind of my master function, and wherever I see my input, I'm going to replace that with my p function. So I start with my p, and I kind of build around it. So the whole long thing is that I have e raised to 1/3 of 3 times the natural log of 2 plus a number, take away 7, increased by 7, finally taking away 2. This problem looks dense, and it is, but it falls apart because of these identities, the additive identity and the multiplicative identities. And I can see immediately towards the end of that raised number that I have a 7, in fact, 0 pairs. A take away 7 plus 7 is the additive identity. So I'm going to rewrite it. E raised to 1/3 of the quantity, 3 times the natural log of 2 plus a number, take away 2. I see that I have the multiplicative identity as well. I have a 1 pair. The 1/3 and the 3 create a 1 pair, and they can cancel out. So I'm left with e raised to the natural log of a quantity 2 plus n, subtract 2. But previously in the other side, I know that e and the natural log are inverses of each other, and when they're used together, that is the identity as well. So they drop out, and I'm left with the quantity 2 plus n, take away 2. And just in the other slide, I rewrote 2 plus n as n plus 2 to make it a little bit more convenient, so I applied the commutative property. I can see much easier now that if I have an increase of 2 and then a takeaway of 2, I have 2 0 pairs created. I have the identity, which leaves me with the quantity n. So on both sides, I have n. I created the identity function. P of q of n, and then q of p of n. This composition of inverses gave me the identity. And it's relaxing and relieving to know that this concept of I use the inverse to obtain the identity is consistent through multiplication, through addition, and now through the composition of functions as well.